Welcome to Quick MCAT Lessons, where I try to explain MCAT topics in 10 minutes or less. Today, we'll talk about how amino acids behave as acids and bases, a concept that connects directly to pKa, protonation, and titration curves. So amino acids can gain or lose protons as they are an amphoteric species. Each amino acid has at least two groups that can either accept or donate protons. The amino group, which can accept a proton and become NH3, and the carboxylic acid group, which can donate a proton and become COO-. Some amino acids also have ionizable side chains, which are R groups that can act as acids or bases. For example, glutamic acid or histidine. Whether these groups are protonated or deprotonated depends on the pH of the environment. First, what does pKa mean? pKa of a group is the pH at which half of the molecules have that group are protonated and half are deprotonated. Think of it this way. When your pH is less than your pKa, the environment is more acidic and your groups tend to be protonated. When pH is greater than pKa, the environment is more basic and groups tend to be deprotonated. Most amino acids have a carboxylic group with a pKa of around 2 and an amino group with a pKa of around 9 to 10. And if the side chain is ionizable, it will have its own pKa too. Here are the pKa's of positively and negatively charged amino acids. I've also included cysteine and tyrosine because their side chains are also ionizable. If a side chain isn't ionizable, it has a specific functional group that can gain or lose a proton at a certain pH, allowing it to exist in different charged states. So the pKa's you should know, most pKa's you can approximate a few to the 10th value of the pKa. For aspartic acid and glutamic acid, I wouldn't approximate too much because you want to know that aspartic acid is more acidic and has a smaller pKa because of the inductive effect of it having one less carbon than glutamic acid. So starting with aspartic acid, the pKa of aspartic acid is 3.86. You can approximate this to approximately 3.9 or 3.8, but I wouldn't approximate it to 4. Glutamic acid is 4.25. You can think of this as about 4.2 or 4.3, but that's about it. Histidine, pKa, you can think of this as 6.0. Cysteine has a pKa of 8.3, but you can think of this as 8. Tyrosine is of 10.07. This can be 10. Lysine is 10.53. This should be 10.5. And arginine is 12.53, and you can think of this as 12. It would also be helpful to remember pKa's relative to each other, and you can do that with a mnemonic. So you can create your own or even use a mnemonic generator. The one that I use is dank emus heckled crazy yellow knights rudely. So you have dank emus, DE, which is aspartic acid, glutamic acid, heckled crazy yellow knights rudely. So histidine, cysteine, tyrosine, lysine, and then arginine. Let's move on to titration curves. When we titrate an amino acid, we add base slowly and monitor how the pH changes. The curve has flat regions called buffering zones where the pH resists change because the group is halfway protonated and halfway deprotonated. This occurs at the pKa. The Pi, which is the isoelectric point, is the pH at which an amino acid has no net charge. Here it exists as a Zwitter ion. A Zwitter ion has no net charge. It exists with a positive and a negative charge, giving overall neutrality. This isoelectric point can be calculated. It's calculated differently based on if the amino acid is neutral, acidic, or basic. So let's go through each one. If the amino acid is neutral, like glycine, you take the pKa of the amino group, you add it to the pKa of the carboxyl group, and you divide it by 2. As I mentioned earlier, the average pKa of a carboxyl group is 2, and the average pKa of an amino group is 9 to 10. So if you don't get the pKa values, you can assume it's 2, and you can assume it's 9 or even 10, which would be, if you add the 2 up, it'd be 11 divided by 2, giving you a Pi of 5.5. In this case, I have the pKa's of glycine, so the pKa of the carboxyl group is 2.3, the pKa of the amino group is 9.6, so you add those up, you get 11.9, and then you divide them by 2, or you take the average of it essentially, and you get 5.95 as your Pi. If the amino acid is basic or acidic, then in the calculation you will use the R group. The other number will either be the carboxyl group or the amino group, depending on if it's acidic or basic. So for an acidic amino acid, let's take glutamic acid. You would take the pKa of the R group plus the pKa of the carboxyl, and you would average this. So I am given that pKa1, my carboxyl group, is 2.1, pKa2, the side chain carboxyl group, is 4.1, and pKa3, the amino group, is 9.5. On questions, they will generally give you all three, and it is up to you to remember if it's acidic and which pKa's you should use. So here we would ignore the 9.5, and we would add 2.1 and 4.1, which would give us 6.2, and then divide this by 2, giving us an isoelectric point of 3.1. The same principle applies with the basic amino acids like lysine. It would be pKa of the R group and the pKa of amino group, and you divide by 2. This is because they have an extra amino group in the side chain. So pKa1, once again, is the carboxyl group, which is 2.2. pKa2 is the amino group, which is 9.0. And pKa3 is the side chain that has a pKa of 10.5. Now, if you ignore the 2.2 and you average the 9.0 and 10.5, you get 9.75. And as a rule, basic amino acids have high pi values, whereas acidic amino acids have low pi values. And this should make sense because basic and acidic amino acids have a charge at physiological pH. So if you bring the pH up all high for basic amino acids, then they won't have a charge because they will get deprotonated. And same for acidic amino acids, they have a negative charge, but if you bring the pH down, way down, then they also won't have a charge because they will get protonated. So just to do a quick overview, amino acids have acidic and basic groups. pKa tells us when a group is half protonated, half deprotonated, and Zwitter ions form at the isoelectric point, which is the pi, and this point can be calculated. It'll be calculated differently for basic, acidic, and neutral amino acids. That's it for today's episode. In the next episode, we'll talk about peptide bonds.